Quicksort is a family of sorting algorithms. From a bird's eye view, the different versions of Quicksort all do the same thing. First, choose a pivot. Second, swap things around so that smaller items are on the left and larger on the right. Third, quicksort each side. But this overview misses the finer details. Details you must know to use Quicksort properly. Let's learn those details together by looking at 1. What makes these versions of Quicksort different? And 2. How does Quicksort compare to other sorting algorithms? The first thing that differentiates these Quicksorts is how they choose the pivot. Let's shuffle these back up to see this more clearly. The simplest way to choose a pivot is to pick a fixed element every time, such as using the first, middle, or last. You could also choose a random pivot, or choose 3 items and take the median of those 3 as pivot. And there's other methods too. Any of these ways to choose a pivot will be fast most of the time, but could be horribly slow. In any case, they'll all get the job done. Our next step is to partition around the pivot. There are 2 well-known ways to do this: Lomuto's partitioning scheme and Hoare's partitioning scheme. To get an idea of the difference, let's watch one round of partitioning for all the different quicksorts. You'll notice each way to choose the pivot can combine with each partitioning scheme, resulting in the family of algorithms we've been watching. After one round, the Lomuto partitions look like this. The pivot is cleanly in the middle. Elements less than or equal to the pivot are to the left, and greater to the right. Hoare's scheme is faster, but it's not so intuitive. Here's how the partitions would be for that. What do you notice that's different? Well, the pivot just goes somewhere in either the left or the right, and other aspects of Hoare's partitioning scheme are also surprisingly tricky. So we'll focus on Lomuto's partitioning scheme for this video. We're going to reason through this step by step, writing some simple pseudocode that we'll convert to real code later. Now, Lomuto's partitioning scheme will work with any pivot choice, but the wrong pivot could destroy your Quicksort's performance. We'll go over how to avoid that problem in a minute. For now, just say we're using this element as pivot. So the goal of partitioning is to get all elements less than the pivot to the left and greater to the right. But how can we do that if we don't know where the pivot will end up? Let's set the pivot aside by swapping it to the high end while we figure that out. We'll swap the pivot back into the pivot's final position once we know where that will be. Then we look at each item starting on the left. Think about if we were sorting an array with only this element and the pivot. Where would the pivot end up? It must be before this bigger element, so in this array with just 2 items, the final pivot position would have to be 0. Which makes sense. There are 0 elements smaller than it, and if we finish now, we'd swap the pivot back to index 0, getting the larger element after it. Look at the next item, and again, imagine what we would do if our array was just these 3. The current item is smaller than the pivot. What does that tell us about the pivot's final position? It tells us that the pivot has to go at least at index 1, since it needs 1 element before it. But we can't have this larger item before the pivot, so swap these 2. In code, it'll be easier to swap current and the item in final pivot position first, and then update the final pivot position. And that's what we do for each item if the current item is smaller than the pivot. Let's walk through 2 more steps to make sure it's clear. This next item is also smaller, so we know our pivot goes at least in index 2, which puts the big element on the wrong side, requiring a swap. The next item is larger than the pivot. Is it on the correct side of the pivot? Yes. Does seeing this larger item change the final pivot position? No. So for bigger items, we don't have to do anything. Continue these steps and you'll see the whole partition gets done, and we end up with the pivot neatly between smaller items and larger items. Now what's that leave out? Yeah, equal items. Recall that after I partition, I quicksort the left and right. Here, when I go to partition the left side, my pivot's going to be equal to the second item. To deal with equal items, we'll adjust this to be less than or equal. Items equal to the pivot will end up on the left side. So that's the basic idea for our partition function, but we've got a few gaps to fill in. If you're serious about understanding Quicksort, pause the video here and try to guess what replaces the question marks. So our top group of question marks is our parameters. How many did you end up with? I'm going to have 4, but 3 is reasonable too. We'll clearly need our array of items. Choosing the pivot is taken care of elsewhere, so we'll just pass in its index. And partition will get called for different sections of the array as I recursively quicksort. So we won't always start at 0 and go to the end. Partition needs to know which part of the array we're doing right now. So send in low and high to specify this range. This next group of question marks is for the initial value of final pivot position. We started at 0 in the example, but we may not start there for subsequent calls. So we should initialize this to low. Finally, what should we return? The main quicksort function will need to know where the pivot ends up to make its recursive calls. So return the final pivot position. And this is Lomuto's partitioning scheme. There's a few details to iron out, but the core ideas are here. If you continue to partition and recursively quicksort, you'll end up with a sorted array. You should be ready to convert this to a real language of your choice, or I'll walk you through converting it to Python in a later video. Nice, right? Now, how does quicksort compare to other sorting algorithms? This is mergesort. It makes sense to compare this to quicksort because mergesort and quicksort have several similarities. Both are divide and conquer algorithms. That is, they both break a problem into smaller subproblems and then solve each subproblem. They're both commonly taught in data structures and algorithms courses as clear examples of divide and conquer algorithms. Both are simple enough to code up for yourself, and both have O of n log n runtime in the average case. However, mergesort and quicksort have some key differences. You may have noticed my mergesort animation moves the sticks back and forth repeatedly. This represents mergesort copying items to a buffer area. So mergesort needs O of n extra space for the buffer. Quicksort, on the other hand, just needs extra stack space for recursive calls. Log n extra space. There's disagreement about whether quicksort is an in-place algorithm. Some people say yes, it is in place because the array items stay in the array. But others don't consider it in place because it still needs extra space. In either case, quicksort has the advantage here. Quicksort may also have better cache performance than mergesort, so that's a second advantage for quicksort. However, mergesort has a couple valuable traits that quicksort lacks. It's stable. This means that mergesort preserves relative order among items that have equal keys. Quicksort is not stable, and stability is often essential, so you'd have to favor mergesort there. Finally, and this is a key one, mergesort always runs in O of n log n time, even in the worst case. With quicksort, on the other hand, you can run into O of n squared time in the worst case. Now that might not seem like such a big gap, but for enough items, it could be the difference between seconds and days. Avoiding big slowdowns means not choosing the wrong pivots, as I mentioned before. You'll want to watch this quick video about pivot choice now to make sure that kind of massive slowdown doesn't happen to you. I'm Coach Slate, and thank you for your time.